I want to start here by using the example that we did yesterday to recap what we did. So remember that in our goodness of fit test, the null hypothesis is that the distribution is what we say it is. So in this case, what we said it was is that the births take place equally across the days of the week. And so that ended up being our null hypothesis here. And then the alternative is that at least one of those proportions is not correct. So that's the way that we're going to go through this. The biggest thing that is different about these tests is that the normal condition is now substituted in for checking that the expected counts are at least 5. And I got those expected counts by knowing that because all the days of the week should be the same probability, that probability should be 1/7. So out of the 140, I should expect a 7th of the 140 on each day, which is 20. So in this case, all the expected counts here are 20, which is at least 5. And then the random and independent conditions were the same. Here's what the formula should have looked like. Degrees of freedom is number of different categories minus 1, so 7 minus 1 is 6. And the p-value ends up being bigger than our alpha level. It's 0.269. We're going to fail to reject since that's bigger than our alpha level. And there's not enough evidence to conclude the local births are not evenly distributed across the days of the week. So now let's talk through how to do this in the calculator. So what you should have had from last time is hopefully you had the data in list 1, and then these are my expected counts sitting here in list 2. They're all the same. So the menu I'm going to go to stat tests, and I'm going to go near the bottom for my chi-square goodness of fit test. And on the chi-square goodness of fit test, we have the observed being in list 1, the expected being in list 2, degrees of freedom. Since there were 7 categories for the 7 days of the week, it's going to be 7 minus 1, which is 6. And then it's going to calculate it for you. Here's the chi-square statistic. Here's the p-value. And these down here are all of the individual chi-square values. So remember that the chi-square is the sum of 7 different pieces. Here's what those 7 different pieces were. It gives you the 2.45 and the 0.45 and the 0.8 and all of these for you. So that's what these are down here. Again, p-value greater than alpha, we're failing to reject. All right, so that's where we look in the calculator. Put the data in list 1 and list 2, and then say where your observed and expected are. That's basically all you need to know for the calculator. So let's look at one more example here for our notes. So this has to do with dominant and recessive genes. So we have tobacco plants having a genetic makeup. Each plant has one dominant gene and one recessive gene. So we have 3 different outcomes here. We have green, which is if both get the dominant gene. Yellow-green if one gets dominant, one gets recessive. And then albino if both get recessive. And so if you remember your Punnett square, what we would expect, this is going to be our null hypothesis, what we would expect is that we have 25% having both dominant, 50% having one dominant, one recessive, and 25% having both recessive. So that's going to end up being our null hypothesis. Now here's our sample where we have 84 offspring, 23 of the plants were green, 50 were yellow-green, and 11 were albino. So I'm going to go ahead and put that in list 1. So clearing out my lists. Now in list 1, I'm going to put those different values here. I have 23 green, 50 yellow-green, and 11 albino. So I'm going to put 23, 50, and 11. 23 here, 50 here, and 11 here. And I will need expected counts to go in list 2. So let's talk about what those would be. First off, let's write our null and alternative. Our null hypothesis is that we have our Punnett square distribution. And then the alternative is that the biologist's predicted color distribution isn't correct. So at least one of those proportions is wrong. So to get our expected counts, well, we have 84 in our sample. We have 84 in our sample. And what we are expecting is that the proportion we expect to be green is 0.25. So we're going to take the 84 and multiply it by 0.25. So in our sample, we would expect on average 21 of them to be green. And then for the yellow-green, instead of 25%, we're expecting 50% of them to be yellow-green. So that's 42. And then for albino, we're also expecting, of the 84, we're expecting 25% of them to be albino. So there is our expected counts. 21, 42, and 21. That's going to go in list 2. Notice for the conditions, which I'll put up in just a second, for the conditions, all of these are at least 5. That's what you're checking instead of your normal condition. Oops, I want my list, and I'm going to put the 21 and the 42 and the 21. So I'm putting my expected counts in list 2. And I'm listing all of them, and I'm saying that they're all at least 5. So here's our step 2. Chi-square goodness of fit test is the name of it. Random. We're coming from a random sample. Expected counts, we are showing out all 3 of them and saying that they're all at least 5. And then independent, we can either say the observations are independent or talk about 10 times the sample size. So that is our random normal independent, or in this case, random large sample size, expected counts at least 5, and independent. Not normal, because chi-squared isn't normal. Step 3, I'm going to go ahead and show the calculator again. Stat over to tests. And we want the chi-square goodness of fit test. The chi-square test, this one, we're going to use in the next section. So not yet. It's a totally different process to do that one. This is the chi-square goodness of fit test, where we have our observed values in list 1, the expected values in list 2, and our degrees of freedom this time, since we have 3 different outcomes, then our degrees of freedom is going to be 3 minus 1 is 2. So there's our chi-square value, degrees of freedom is 2. There's our p-value. Oh, it's 0.0392. That's less than our alpha level 0.05. So we are going to reject our null hypothesis. So here's all those details. Again, degrees of freedom is number of categories minus 1, so 3 minus 1 is 2. Here's the formula. Observed minus expected squared over expected. This should be a 42 here. 42 instead of the 50. Expected goes on the bottom of the formula. And then p-value is less than our alpha level. Reject the null hypothesis. There is enough evidence that the distribution is incorrect. Now, all we know there is that the distribution is incorrect. It does not say, no. All it says is that the distribution is not correct, but it doesn't say which parts differ from what we expect. To do that, we have to go in and analyze the data a little bit more. And the way that we're going to do that is by figuring out which parts differ the most from what we expect. And the way that we're going to measure that is by looking at each of the components of the chi-square formula. So remember that on the calculator, it gave us each of the contributing chi-square values. So this one was 0.19, and then I have the second value is 1.52, and then this third value is 4.76. The larger the chi-square value, the farther away the observed and the expected are. So larger chi-square values tell me it contributes more to the chi-square statistic being larger, and is probably the thing that is causing us to reject the null hypothesis. So there's our culprit, because it had the largest chi-square statistic of the three pieces. That is where our value differs the most from what we would expect it to be. So we do that if we're rejecting the null hypothesis. And we take a look at what the chi-square values are and see which ones differ the most. All right, so that's everything in your notes. Now, what we're going to do next is we're going to look at a free response. So I'm going to pull out, it should be the file that says week 21. And that's going to give us a couple practice free response questions. We're going to jump to question number 3 of those free responses. So we're going to look at number 3 here. And we have a lovely game show here where we are going to spin a wheel. And if the result is a skunk, no money is won on the contestant's turn. It's finished. That bankrupts you. If we get a number, then we win that amount of money. And we get to spin again. We get a chance to spin again. So we are deciding whether we want to keep going and try out our luck, or whether we want to stop with the money that we have. Because if they spin again and the result is a skunk, then all the money is gone and the turn ends. So the contestant may continue adding to the winnings until they choose to stop, or until a spin gives a skunk. So we can keep racking up money for as long as we don't get a skunk, and we can stop at any time. That's the name of the game here. So let's ease back into a little bit of probability by answering some basic probability questions here. Part A. What is the probability that the result will be a number on all of the first 3 spins of the wheel? Well, probably the result will be a number. Well, let's find the probability of a number on the first spin. So on a single spin. Well, on a single spin, we have 4 different outcomes, and it says that outcomes are all equally likely. And how many of them are numbers? Well, 3 of them. The 200, the 100, and the 500. So we have a 3 out of 4 chance of getting a spin that gives a number and not a skunk. So to extend that, the probability of a number on all 3 spins, well, in order to do that, you're going to have to get a number on the first spin and multiply, and get a number on the second spin, and get a number on the third spin. So we just multiply them because each outcome is independent of each other. So that's part A. Over on part B, suppose a contestant has earned $800 for the first 3 spins and chooses to spin again. What is the expected value of the total winnings for the 4 spins? So on part B, I'm going to make a table here. So we won $800 so far. And I know I'm told that all the outcomes are equally likely, which means they're all 0.25. And what are the 4 different outcomes? Well, I have $800 in the bank so far. So I have $800 in the bank, and so I could add to that. If my spin landed on 100, then I would add to that, and I would have 900. If my spin lands on a 200, then I add to the 800 I already have to be 1,000. If my spin lands on a 500, then I add to the total that I already have, and I have 1,300. If my spin lands on a skunk, then oh no, we went bankrupt and we have nothing. So to get our expected value here, remember that formula for expected value is value times probability of it happening, and then we add all those together. So 900 times the probability of 900 plus 1,000 times the probability of 1,000 plus 1,300 times the probability of 1,300 plus 0 times the probability of 0. So that is our formula for expected value. So that's part B. Now, quick little basic probability review there. Part C, this is where the chi-square test comes in. A contestant who lost at the game alleges shenanigans that this wheel isn't fair. And so since we are alleging shenanigans, we are making a conclusion whether the 4 outcomes are not equally likely. Well, that means that our null hypothesis is going to be that the 4 outcomes are equally likely to happen. So our null hypothesis should say something like all 4 outcomes on the wheel are equally likely, or all 4 proportions are 0.25, like we had put on the table before. And an alternative is at least one of those values is incorrect. Let's get our expected counts. Expected counts. Well, that's actually pretty easy because we're taking 100 spins of the wheel, which we're going to treat as our random sample. We've already got our outcomes being independent. It says that at the top of the question. So we want to know what the expected counts are because we want to check that there are at least 5. And we want to put them in our calculator. Well, if all 4 outcomes are equally likely, that means they all have a 25% chance of happening. And so if I spin the wheel 100 times, then I should expect 25 of them in each value of the wheel. So there are my outcomes that I would expect. So we're going to take those observed values, the frequencies, and we're going to put them in list 1, and then I'm going to take those expected counts of 25, and I'm going to put them in list 2. So let's go through and do that here. Stat edit. Now my values that go in list 1 are 33, 21, 20, and 26. And while I'm doing this, you should be following along and making sure that you can get the chi-square statistic and the p-value and that kind of stuff ahead of me here. By this point, you should be able to do it on your own. Over in list 2, They're all 25. Those are all my expected counts. And they're all at least 5. So that's good news for us. There's our condition of the expected counts being at least 5 met. So then I'm going to go over stat. Over to tests. This is a chi-square goodness of fit test. Degrees of freedom, it's the number of categories minus 1. Well, we have 4 different categories because we have 4 different possible outcomes. Minus 1 is 3. So there's my chi-square statistic. That's the p-value. And here are the 4 different chi-square values that we're adding together. So that should give you a couple of different examples to look at. Remember, your null hypothesis is going to look like the distribution is what we think it is. And so what that actually is in context will depend on what we think the distribution is. So for the M&Ms, there was a very specific distribution that the company said that the candies were in. So we used those very specific numbers, and each of them were different for the different colors. When we had our days of the week example, it was based on, all the days of the week are equally likely. So then all the expected proportions were the same. When we had the biology example, we based it on the Punnett square. So we used those Punnett square values of 25%, 50%, and 25%. So it'll just depend on the context of that problem. So you got a book assignment. You should be able to get a good start on it here this weekend. We're going to start our next section here next week.